Okay, so after all these problems, I hope we now can start. And as we discussed last time, I will explain the finite element method by starting with the one-dimensional problem, as you can see here. So we have the second spatial derivative of u just with respect to x. U is just a function of x, is equal to some right-hand side, to some excitation. This would be the notation for the general three-dimensional case where we would have minus the Laplacian on the unknown solution quantity u depending on x, y, and z. Okay, so since it is 1D, we have a computational domain which should be starting at x0 being a value a and ending at xm being or having a value of b. And we have, and that is important, as you know, not only the differential equation, but also the boundary conditions has to be specified on each boundary, which is here the left boundary and the right boundary. These are just 2 points in 1D. And as you can see, we have defined here a fixed value of our unknown function u at the left boundary being ua and at the right boundary being ub. Okay, so we have everything. We have our partial differential equation, in our case, just a differential equation because we have just one coordinate here. We have the boundary condition and we have the computational domain. As I already discussed last time, the main point for the finite element method is that we first go over to a so-called weak, sometimes also called variational formulation. So we do not discretize directly our partial differential equation. Instead, what we do is we choose a so-called test function, multiply the partial differential equation with this test function as shown here. So I have put the excitation term to the left-hand side, integrate over the whole computational domain. For us, it's from a to b. We have just this line integral from a to b because it's one-dimensional, and that has to be equal to 0. It's clear because we also have here, let's write it in this sense, the strong form would be the second derivative of the unknown u minus f is equal to 0. Yeah? So you see, the starting point is that we multiply our equation with a test function, integrate over the computational domain. Now, what we'd like to relax a little bit is that we have here a second order spatial derivative, which would mean, for example, if we use a linear approximation for u, that this would give us 0, because it's a second spatial derivative. However, if we use the integration by parts, and we will see in the general three-dimensional case that we will use there the Divergence Theorem. Now, by this integration by parts, we have our boundary term, which is then just v and the first order derivative of u to be evaluated at the boundary of our computational domain at a and at b minus, and the remaining integral we now have the derivative also of the test function with respect to x, and instead of the second spatial derivative, we have a first order spatial derivative on u. So we see that a main point is that here we have now just a first order spatial derivative on the unknown function u. So the weak form, to be now precise, is as follows. We have here on the left-hand side now the integration over the first order spatial derivative of the test function and the unknown u is equal to the right-hand side, where we also have this integration over the computational domain, the test function multiplied with the excitation function f. What is important is that when we speak here appropriate test function v, that this test function is 0 at the Dirichlet boundary. Why this makes sense? Because we already know our unknown physical quantity u at Dirichlet boundaries. Yeah? We know that u at position A is ua and u at position B is ub. Therefore, our test function v is set to 0 at any Dirichlet boundary we have within our computational domain. Yeah? So since this is 0, yeah, the whole term here is 0, and this term doesn't pop up in the weak formulation. Please keep in mind, if we have a boundary condition which is a Neumann boundary condition, where we have the first order derivative of our physical quantity, that there the test function should not be 0, because at this boundary we know the normal derivative but not the function itself. Okay, we will come up to this later on, but as you know, we have here to solve a partial differential equation with boundary condition which are pure Dirichlet boundary condition. Okay, so that means the weak form is that we now have to solve this equation here, and in addition, u should fulfill the Dirichlet boundary condition as written here. The main advantage again is of this weak formulation that we now just have the first order derivative on our unknown quantity u. In most cases, so clearly what is important to say is that this weak formulation, and the weak formulation is really also including the Dirichlet boundary, that this weak formulation is totally equivalent to the strong formulation, which is our partial differential equation, or ordinary in this case, and the boundary. Yeah? So this together we also called the strong form of our problem. So there are no approximations. The approximation starts then clearly when we will discretize the computational domain, as shown here. So step 2 means that we have to discretize our computational domain. In our case, in 1D, it is just a line. And this can have any irregular discretization. So here, this parameter h could be different for each element we have here, or it is the same, so that is up to us how we do the discretization. And clearly, the computational mesh, which is very simple in our case, as we see here, we just discretized here this line here with our elements, that we have ascending order of nodes. So the coordinates of node I minus 1 should be smaller than the coordinates of the node I. And clearly it should be complete in such a case that we do not allow overlaps, and clearly also no holes. Okay, so this is just what we have here with the domain discretization. So here we just summarize this domain discretization. In our case, make it simple. that we have here a mesh size which is the same for each element we have here. So this is, as we will call then, a finite element. And here the positions we have, we will call a finite element node. These are our finite element nodes at which we want to compute the unknown u we have here. That also means it's very similar as you do the discretization or sampling of a time signal when you have an analog digital converter. It is now clear that due to this discretization, we, in a first case, we clearly get away the information what is between these two nodes. How does the solution change between these two nodes? That is discretization. And as we have to fulfill Shannon's theorem, when we discretize a time signal, we also have clearly to have a discretization in space, which is accurate enough, so small enough, such a finite element, that we get all the different solution behaviors into account. Okay, so that was step 2, where we did the discretization of the computational domain. And step 3, we now, and that is important, we approximate the physical quantity. And as you can see here, we write it in this way that the continuous solution, as we have, u of x is now approximated by a discrete one. And the discrete one is a sum of so-called basis functions, and we call basis functions, and the unknown physical quantity at each finite element node, where we do not know the value in advance. We know the value in advance at the left boundary and at the right boundary, and you see that we also apply there a basis function and multiply it with the correct value we have for our physical quantity at the boundary on the left and the boundary on the right of our computational domain. In order that this can be done, this ansatz can be done, we need this property, which means when you evaluate now your discrete solution on a finite element node, then you want to get out exactly there this ui. So this, for example, then at this position, let's say this is the node I, then here you have the unknown physical quantity with index I, and clearly if you have such a sum, it just can't be the case that you get out ui when you have this property. And then you can write your approximate solution as the sum of all these basis functions scaled with the unknowns at the finite element. So this is a very important property we need, which also will show us that this basis function will have local support, so they will be just different from 0 in the environment of the node itself. And that is shown here. So again, step 3, the approximation of the physical quantity. Let's write it also here. So this is node I. And as you can see, this basis function ni is exactly 1. Has to be the case, otherwise this would be not correct. So ni at the node I has the value 1, therefore we get out ui, and it has to be 0 at the neighboring nodes. And that important property we call local support, and that means we can also write the evaluation of such a basis function at any node xj, that this is the delta function. Yeah, so it is 1 if I is equal to j, and it is 0 when they are different. And that is what we see here. Yeah? So this basis function in I is if it were 0, then it is a straight line going up to 1, going up to 0 at the neighboring node, and it keeps the value 0 at all the other nodes of our computational domain. Okay, so step 4 would be now the substitution for the physical quantity and test function. So you see, we also discretize the test function with the same basis functions. And as you can see here, we just need this for nodes from 1 to number of nodes, which is capital M minus 1. Yeah? Because at these boundaries we have here of our computational domain, so this is the node 0, and this is the node with index M. We don't need, because there our basis function, our test function is 0. And for the physical quantity, I just have rewritten it on this slide. It is again for node j equal 1 to m minus 1, where it is unknown, and it is known at node 0 and node m, so node 0 and node m, where we know the value already due to the directly boundary condition. Okay, so now we take these approximations. Yeah? The h here as the superscript means this is the approximation for the continuous test function. This is the approximation for the continuous unknown physical quantity. And that we now take and put into our weak form. So the starting equation is our weak form. That was the continuous one, still in the continuous space. And now we will approximate the test function v and the unknown u by this ansatz as shown here. Okay? That means we put it in. So we have to put in for the test function this sum here, and for the unknown physical quantity, this larger term, which also includes the directly boundary condition UA and UB. And on the right-hand side, I just have put this term on the left-hand side. We also have here to approximate our test function V by this sum over NIVI scaled with the excitation function we have integrate over the computational domains. Yeah, and now we can do a lot of steps in order to rearrange terms. So the first one clearly is you can put the sum here out of the integral. Furthermore, this spatial derivative you have to apply on such a product. Yeah? And if you look on this product, then just the basis functions are functions of the space, because the test functions at all the finite element nodes or the unknown physical quantity at the finite element nodes, they are constant, yeah? Because they are the unknowns at these nodes, but they are no functions of our coordinate x, which means when we apply the derivative on this product, it is just a derivative on the basis function. So that we will see on this slide. So first step, as I promised to you, we put out here the sum in front of the integral. We can also put out vi out of the integral. We even can put uj out of the integral because they are constants. And you know, when you do an integration, all constant terms you can put in front of the integral. So you see what remains here actually is really this term here, the partial derivative of the basis function ni with respect to x and nj with respect to x, and integrate over the whole computational domain. We have here this additional term where we have here the Dirichlet value at the left boundary and the Dirichlet value on the right boundary. And we should not forget that we also have our excitation term, which is shown here. Here is the parenthesis, as you can see, because this depends on ni, and all these terms depends on ni and nj, as shown here. Okay, now you see, when you fix I, for example, this I, then you get one equation. Yeah? So, for example, I equal 1. Yeah? Then what you have here is everywhere where the index I is substituted by 1. But you also have the index j, which goes from 1 to m minus 1. So you get one equation which has to be 0. In the next step, you can go to I equal 2, and you will again get one equation here, individual equation here, where I is fixed to 2. And that you have to go up until m minus 1, which means you have m minus 1, m is the number of nodes, m minus 1 equations, and that you can write in a very compact way, as shown here, with, let's say, the sum, or even that we have a system matrix which includes all our terms with which the individual unknowns u at all the finite element nodes where it is unknown is multiplied is equal to a right hand side, and the right hand side is a vector again with dimension m minus 1. So what we have now turned over is that at the end we have here a system of equation with a system matrix, a vector of all the unknowns, and the right hand side, which is computed out of this term. And don't forget, there will be additional values according to the Dirichlet boundary conditions, which will also enter the right hand side, because all the terms we have here we know. Why does the test function vanishes? Somebody has an idea why the test function vanishes. You don't see anymore the test function. And it is not within the system matrix. Perhaps before we answer this, you see the system matrix in our case is very simple, because it is just this term which is multiplied with uj. Uj are the physical quantities at all the nodes where we don't know the solution, which means in our case this is our system matrix. Very simple how we have to evaluate it. And you see a little bit more difficult is to compute the right hand side, because we have, in addition to the source term where we have the excitation F, also to include somehow our Dirichlet boundary conditions UA and UB. Okay, now you have seen. So in the system matrix, it doesn't pop up. On the right hand side, it doesn't pop up. So where is the test function? Exactly. So as I have told you, we will have m-1 equation. The first equation is just multiplied by v1, but we are not interested in the coefficient of our approximation for the test function. I go here back. So this we can also name as a coefficient at all the finite element nodes for our test function, and we are not interested. We are interested in the physical quantity. Exactly. Okay. So you see that this test function was very helpful in order to transform from the strong form to the weak form, but at the end, on the discrete level, it doesn't pop up, we don't need it, and we end up in a system of equations with a system matrix, the vector of all the unknowns of our physical quantity, and a vector of the right-hand side. Yeah, and we will go in some details, but before we go in the details, we should have a look to our system matrix, which has a very nice property, as you can see here. So you see, clearly importantly, otherwise you would have not a definite matrix. On the diagonals, clearly, we have entries, and then for a standard diagonal entry, you have a left and a right entry. But all the others, as you can see here, are zero. So you have a lot of zero entries. And that clearly we know has to do with the local support of our basis functions. Yeah? We will go in detail to this, but that we already see here, yeah? Nicely. Or if you look n0 and n1, you see they just have an overlap. This basis function n1 just has an overlap at the node itself clearly and the two neighboring nodes. So that means for all the other nodes it is zero, and so you just can have a diagonal entry and two off-diagonal entries, because for all the other nodes it is zero, and that gives you this so-called sparse matrix. So you call this a sparse matrix, and that makes clearly the finite element method very efficient towards a solution process, because we have very special algebraic solvers who can solve such a sparse system of equation very efficiently. And towards storage, it's great because we will never store all the zeros. We will just store the non-zero entries, and for a general equation, just 3 of them has to be stored. Yeah? At the start and end point, just 2, the diagonal and 1 off diagonal. But if we look at all the other entries here, we will always have a diagonal, a right and the left entry being different from 0. Yeah, one question. Do you think the system matrix is symmetric? So I can show you here. We know that all the entries we have are computed by evaluating such an integral. Do you think it's symmetric or not? So also those, please write it in the chat who are online, or switch on your microphone. Those who are present, okay. Okay, so you think, yeah, it's somehow clear, because if you exchange I with J, what should be the case? It has to be symmetric. Yeah? We will see it, because we will now, for a simple example, explicitly compute the entries of the system matrix and the right-hand side. Somebody knows why it is symmetric. At which point we already know if we have a symmetric system matrix or not. You have an idea. Okay, perhaps this is not so easy. Actually, it is the starting point. Yeah, you need a differential operator like this, and then you will get the symmetric matrix also. Yeah, perhaps it's easier when you look at the weak form. Yeah, so this gives you the system matrix at the end when we do the discretization and the approximation steps. But you see, you can also exchange here V by U. Yeah, so here it is easier to see it. What will be a problem, and that perhaps is not fully understandable for you if you are not involved in partial differential equations. But in this case, yeah. Okay. So if we would have, we had this minus du squared, the second derivative with respect to x. And then I could put here plus some given v0 du dx. Is f, for example. Yeah, and then we have some boundary condition. So you see what we have here. Let's say this is a given velocity. Or any given parameter. Yeah, that is given. But what you see here is the following. You have here just the first order derivative. Yeah? Now, if we and let's say boundary condition to make it simple is equal to 0 on the whole boundary. Yeah. So this is our partial differential equation on the whole volume. Again, it's just a line because we have a one-dimensional problem, and with a simple boundary condition u equals u. So if you have already a lot of knowledge about partial differential equation, it would be clear that this operator is a non-symmetric operator at the end. Yeah? But it's easier if we turn over to the weak form. Yeah? What we have to do, we integrate our partial differential equation over the computational domain. Therefore, I write omega here, which would be for a 1D problem, let's say again from A to B. We have the test function, and let's write down our differential equation. Integrate it over the computational domain, and that should be 0. Yeah? And now you see actually what we have is we know that we can rewrite this as follows, as dv dx du dx dx. Let's say this is our first term. So we have used here the integration by parts. Since u is 0 on the boundary, the rest will be 0. And then we have here this integral where we have any coefficient v0. We have the test function du dx dx and minus integral test function f dx equal to 0. So this is our, just as we call it, right hand side, or as you call it, RHS. Okay, and here you now immediately see it. Yeah? Here you can exchange v with u. There will be no change. Here you cannot exchange the test function with the unknown physical quantity. It would be something different. Yeah? So you clearly see this will give us a non-symmetric non-symmetric entries, and therefore also the system matrix, after we will do the discretization and approximation step, a system matrix which will be non-symmetric. So, by the way, why I have named V0 a velocity, because such a term is called a convective term. Yeah. And that we have, for example, in the heat equation, you clearly have it for flow dynamics and so on. We even have it for electromagnetics. If you have moving bodies having a conductivity, electroconductivity different from zero, we also could have such a convective term, which gives us the motional electromotive force, yeah, in our model. Are there any questions concerning this part here? So you see, that was now a different differential equation, but the steps to come up to the weak formulation are again the same. Yeah. So you multiply with the test function, and everywhere where you have second order spatial derivatives, you apply an integration by parts. You could also apply integration by parts to this term. Why not? It's possible, but it will not change anything. And then, okay, you have u directly and a spatial derivative of the test function plus some boundary term. Yeah, but you don't gain really something. Yeah, sometimes it could make sense for some partial differential equation, but in general, if you just have a first order space derivative and this is scaled with the test function, you will not do an integration by parts. You just let it as it is there. Okay. So that was already everything for the finite element method. Yeah, it will get a little bit more complex in 2D, and 3D is not more complex as 2D. There will be really a step from 1D to 2D, but these are the steps you have to do. And for all those who have some knowledge in the finite difference method, you see that this is really different to finite differences. You directly do an approximation of the differential operator. Okay, now let's have a look how we compute the entries of our system matrix. Okay, so what we have here is the following. I show you also here the sketch. This is our computational domain. This is the node I. This is the node I plus 1 here, and this is the node I minus 1. Yeah? And for example, such an entry as I minus 1, yeah? Because as you know, we have to evaluate here the entries. I means one basis function is at node I, and the j means this is the basis function at node j. And what you also see here already, we don't integrate over the whole computational domain. Yeah, makes no sense because they all have local support. Yeah, and therefore it's enough when we integrate here from this here from x minus 1 to xi. Let's look, because once we have the basis function n minus 1, and I make here this explicit. And when we have the basis function in I make this here explicit. So they just have, as you can see here, an overlap from node I minus 1 to node I. In all other regions of the computational domain, they have no overlap. So it's not necessary, yeah, and that also brings a lot of efficiency then, especially when you think to 2D or 3D, we do not compute for the entries and evaluate the integral over the whole computational domain. Just over these small domains where the basis function as shown here have an overlap. Yeah? And since they just have the overlap between the node I minus 1 to the node I, there is the coordinate xi minus 1 to the coordinate xi, we just evaluate the integral here along this part of the computational domain. Now, what you see, we need here the derivative of the basis function ni with respect to x, because x, well, we just have one space coordinate. This is ni, yeah? So ni has a positive slope and then the negative slope. And everywhere else it is 0, yeah, as we know. So the derivative here gives you, since it is a positive slope, and this is 1, yeah, here just 1 over h, yeah. So h is our discretization, and we have applied a uniform discretization, yeah. So that then in this case clear, and you see it here. We have here 1 over h coming from this term. Ni minus 1 is this, the basis function positive slope, negative slope. Yeah? But we are within this part, I minus 1 up to I, so we have a negative slope, and that's clear why now the derivative is minus 1 over h. Okay. So we have minus 1 over h squared. If you integrate this accordingly, then at the end, because the difference xi minus 1 is h. Yeah. So the integral, perhaps I rewrite it here. The integral would be minus 1 over h squared, x to be evaluated at xi minus 1 to xi. Yeah. And the difference xi minus 1 is h. Yeah? And that is why our solution at the end is minus 1 over h. And now you can exchange I with I minus 1 and you will get the same solution. Yeah? And that gives us the symmetry as we just have discussed. Okay. So what remains is a diagonal. So this was an off-diagonal entry, and we see the symmetry. Now we also have to compute it for a diagonal entry. Well, now we have to be careful because I make it in green. Because ni, yeah, ni is this one here. Yeah, and then it is 0 to the left and to the right. So you see it is different from 0 from the node I minus 1 to the node I plus 1. Yeah? That is why we subdivide the integral into two integrals from position xi minus 1 to xi plus the integral from xi to xi plus 1. Okay, now from xi minus 1 to I, we have the positive slope, as you can see here. One moment, before we do this, yeah, very good question in the chat. When the basis functions are differentiable, very good questions. Yeah, because actually you call this basis function also hut functions. They are like a hut. Yeah. Yeah, they are not differentiable in the strong sense. It's clear because at this point, well, what do we have? I will go to this additional slide. So let's make it explicit. We have such a hard function. Here is x, and we call this f of x. Yeah? And now it is clear when you do the differentiation, yeah, so we have f prime of x, then it would be, let's make here -1, +1, and the value is 1. So we don't have to think over what is the when we differentiate, then it's clear it is 1 coming from the left, and then it goes here. It's too, sorry. I should make it like this, and then it is clear. So now let's make it in green. So you see here it is 1, here it is -1. But what about the value at x equals 0? So it is in the strong sense, as you have learned in mathematics or any other course, it is not differentiable in the strong sense, but it is differentiable, and now it comes in the weak sense. Yeah, because we have here in addition that this differentiation is within the integral. And there you can prove that it is differentiable. In the strong sense, if you do not have the differentiation within this integral, it would be not possible. Yeah? So the strong sense was exactly what we have just discussed. Yeah? That is the strong sense. You have a function and do the derivative. But at x equals 0, it's not clear what the value is. So it is in the strong sense not differentiable. But in the weak sense, because we have it here. There is multiphysics 2, where I go also a little bit towards functional spaces. Actually, the functional space we need here are Sobolev spaces. And there I will also give you the proof why this is really differentiable in a weak sense. But in a strong sense, very good question in the chat, it is not differentiable. But that also gives us a plus for the finite element method, that due to this transformation to the weak formulation, we can use, as we have here, these hard functions, yeah, we can use it, which would be not possible in the strong sense. Yeah, clearly, because this hard function in a strong sense is not differentiable. Okay, very good. So I have now seen this in the chat. Okay, so you see, and that is also the case, so that very fits your question also what we are doing here. So you see what we actually do is we don't integrate from position xi minus 1 to position xi plus 1 because we would have a problem with the differentiation. But I can subdivide the integral from xi minus 1 to xi plus xi to xi plus 1. And in this part here, we can differentiate. Yeah? And the differentiation is always 1 over h. In this part, from I to I plus 1, it is always minus 1 over h, yeah? As we have written it here. So you see at the end, if you do and evaluate this, you get out here 2 over h. So you nicely see, and that gives you a special property to the system matrix. The diagonal entries are positive and the off-diagonal entries are negative. Yeah, that gives you a very special property, and you can use standard solvers. Okay, now let's have a look to the right-hand side. So for the right-hand side, I have assumed that our f is equal to 1. And then you just have to integrate here the basis function we have here for an entry at position I of the right hand side from xi minus 1 to xi plus 1, because for this domain, as we have seen here, for the green part here, we have here a value of the basis function being different from 0. So if you evaluate it, you will see at the end, you get here a very simple value out, which is equal to h. Okay, if you explicitly compute the entries, we need some values. Let's say we have the following. The computational domain has a length of 10. We subdivide in 5 elements, which means each finite element has a length of 2. Let's say this is meters or centimeters, whatever you use. And then you see how nice the system matrix is. You have ones on the diagonal, and all the off-diagonal entries are minus 1 over 2. And as we see here, since the right-hand side gives you an entry of h, when f is equal to 1, the right-hand side is always 2. Yeah? And what we have assumed also here, so I have to write, I've forgotten here, we have assumed that UA is equal UB is equal 0. So we had homogeneous Dirichlet boundary conditions. Did you also see here the plotted solution? The value is 0 at the left boundary and on the right boundary. For this special differential equation, it is really the case that the discrete solution are exactly on the analytical solution. But this is just for this simple differential equation we had. Yeah? But it's a nice property, so you see, okay, yeah, due to the discretization, well, we have here clearly and the linear interpolation between the nodes, we clearly have a difference to the analytic solution, but at the nodes where we have computed our physical quantity, it is exact the analytical solution. Very nice property, which you have exactly for the Laplace operator. Yeah? And that was the 1D Laplace operator. If we go back to our convective partial differential equation, as shown here, you already will lose this property. Due to this convective term, you will see that for this partial differential equation in the discrete form, also in 1D, the solution of the discrete system of equation will not be exactly at the analytical one. So this is just for this Laplace operator property. Okay, and now you can see it's very similar as you would have any function, and this is the time, and you do a sampling of this time function here. It is just over the space. Yeah, if you really want to get the accurate solution, you need more nodes. Yeah, because actually we have lost information which is between these two nodes due to the discretization. That's the same if you do a sampling of a time function with an analog digital converter. You also don't know what is exactly the value in between. And that also will show you the following. If you have a solution where at some positions you have a large gradient in the solution, so the solution changes strongly, you need a finer mesh at this position, at the other position where the solution is very smooth. Not easy because you don't know the solution when you start with solving it with the finite element method. But it gives you then an idea, if you have the solution and you look at your solution, where you have to refine your mesh and where you can keep the mesh. Yeah? And there are clearly also some automatic methods where you really have an error estimator after the first solution you have obtained with your first mesh. The error estimator will indicate where you should refine and where you can keep your mesh, or even can coarsen your mesh. Yeah? And that are then adaptive methods, which is beyond this coursing. Okay. Any other questions? Okay. Then we can also start today with the extension to 2D and 3D. And the first part is more or less the same, but as you know, the integration by parts in higher dimension, higher than 1D, we apply there the divergence theorem. Yeah? And then we will also have in not only volume integrals, but also surface integrals. Okay, so what we are considering here is again a Laplace equation where we have a material parameter, and very importantly, we assume that the material parameter depends on the space. Yeah, it could be even that you have two subdomains and the material parameter is constant but different. Yeah, in space 1 as in space 2. Could be a iron-air interface, for example, in computational electromagnetics. And you will see that this will be no problem. However, in the strong form as written here, well, it is not so easy because you know you could rewrite this as minus the gradient of mu dot product with the gradient of u minus the material parameter Laplacian of u equals 0. Yeah? And now you see, in the strong form, you have to take a derivative on your material parameter. If it is a smooth function, no problem. But what happens at the interface where the material parameter immediately jumps? Yeah? As we have in electromagnetics, from iron with a very high permeability to air with a very low permeability. Yeah? What you have to do there, and there you need some additional effort within the finite difference method, but no problem within the finite element method, as we will see. And then make it a little bit more general. We have a Dirichlet boundary condition as shown here, and we have a inhomogeneous Neumann boundary condition as shown here. Gamma is the boundary, index n actual means, the n here means neutral, and E means essential. We will see, because any Neumann boundary condition we can incorporate in the weak formulation. The Dirichlet boundary condition is not incorporated. So we have, in addition, also to fulfill not only the weak formulation of the equation, but also the Dirichlet boundary condition. Okay, now let's jump in. As I have told you, the same as in 1D, we have a test function. Test function again, 0 at the essential boundary condition, because there we are not interested in our solution because we already have the solution. Yeah? We multiply this test function with the partial differential equation, and since the right hand side is 0, this is equal to 0. So what you see here now, in order to make the next step clear, material parameter multiplied by the gradient of u is any vector f. Yeah? And then you see, actually, we have the divergence of a vector f, and that clearly gives us the idea that we will use the integral theorem of Gauss, or divergence theorem as it is. Okay, here it is explicitly written, what I already have also evaluated before. So if you have the divergence of a scalar quantity, our test function, and a vector, it is the same as the gradient of the scalar function, which is v, our test function, dot product with the vector f. And in addition, we have here the scalar function, which is our test function, multiplied with the divergence of f. Why we explore it is clear, because what we have here is this term here, and we want to do on this term multiplied by the test function an integration by parts. And this is exactly what we have here. So this is the term which we want to get rid of. Yeah? Because behind f, as we know, going back, right, behind f is the gradient of the unknown u, and then we would have a second order special derivative, yeah, and that we want to get rid of. Okay, so that means if we now, perhaps I should write it down here so that it is also easier to follow for you. So our f is our material parameter and the gradient of u. So now, as you can see, this term can be substituted by this term and this term here. That is why we have now this volume integral, yeah, because behind f is the material parameter gradient u. Now what you see, you have now the gradient of the test function dot product with the gradient of u, and you have no derivative on the material parameter. That is a very important thing. Yeah? So now your material parameter can jump at any position within your computational domain, because we got rid of it without approximation. We have done no approximation. In addition, what remains is clearly this part here, where we have to take the divergence of the test function material parameter gradient of u. And you know, the divergence of a vector can be rewritten and integrated over. The volume can be substituted exactly by the closed surface integral of this term itself. Okay, so that is why we now have, when we apply the divergence theorem, we have here that this term is now substituted by this volume integral, which we already had here, and out of this volume integral we got by the divergence theorem this closed surface integral. Yeah? And now if we look at this part here, it's clear. Again, we just have first order derivatives on test function unknown u, and also here unknown u. Don't forget that there is a dot product with the normal vector. Okay, so that means that our weak formulation is as follows, as written here, that we have this volume term where we have the gradient of the test function and gradient of u, and directly the material parameter. Then we have our closed surface integral, which we split into the part of the surface where we have the essential or Dirichlet boundary, and where we have the Neumann or natural boundary. Well, this term is zero. Why? Yes, exactly, because we have chosen a test function which is zero at a boundary where we already know the unknown u, the Dirichlet boundary. And you see that here on this boundary, we already know this term, yeah? Because if I go back, here we have this result that material parameter gradient of u in normal direction is equal to Qn. Yeah. So you see, we naturally can put in here for this term Qn. Yeah. So this Neumann boundary condition naturally enters our weak formulation, and at the end it is a known term. Yeah. Because the test function we know we get rid of when we do the discretization, go over to the discrete form. And this term here we know due to the boundary condition. Yeah. So this is just what I have explained to you now with a lot of sentences is written here. Which means at the end that this is our weak form. We have again, as we had in 1D, this simple term here, in our case just, it is not only the special derivative with respect to x, it's also with respect to y and z, so we have the gradient of test function dot product with the gradient of u, and this boundary condition on the natural or Neumann boundary is a kind of an excitation now for us. Yeah? And clearly, we should not forget, we also have to fulfill on the Dirichlet boundary, the Dirichlet boundary condition. What we have again gained, very importantly, is just here, we just have first order spatial derivative. So again, we can use such hard functions, yeah, which would be not possible, okay, not possible in the strong form, because such a hard function cannot be differentiated in a strong form. Okay, then use any other linear function is also not possible because you have a second order spatial derivative. Yeah? And that gives you 0. So you would need at least for the approximation here, when you do it directly in the partial differential equation, a function of second order. All other things will make no sense. Okay. Yeah, I think that's a good time to stop, I would say. Otherwise,